Hello, my name is Arthur Negrão, and I will be your guide today on Benford's law as a distributional prior for post-training quantization of large language models. Quantizing a large language model means replacing its high-precision weights with a much smaller set of values. Going from 32 bits to 4 leaves only 16 representable levels, for example. So the question is, where should those levels be placed? Round-to-nearest quantization places the levels uniformly across the range. However, transformer weights do not occupy that range uniformly. Many values instead lie close to 0, while a few extremes determine the scale. We therefore spend levels in sparse regions and introduce larger errors where distribution is dense. A log-spaced grid instead concentrates levels near 0. This motivation comes from Benford's law. The probability that the first digit is d is the base 10 logarithms of 1 plus 1 over d. So the digit 1 appears about 30% of the time. Equivalently, fractional logarithms of the magnitudes are uniform between 0 and 1. This suggests a broad range of scales. It motivates the prior, but does not prove optimality. A way to update combines a multiplicative term with an additive residual. When the multiplicative term dominates, the logarithm turns multiplication into addition. Optimizer and gradient variations then resemble a noisy random walk in log space, spreading weights over several scales. The paper tests this layer by layer. Linear weights in attention and feed-forward blocks closely track Benford. Layer norm, however, contrasts sharply. Its parameters occupy a narrow scale and concentrate on one first digit. 4 of 6 models pass the 20% Benford test, motivating us to quantize transformations while preserving layer norm. Bank is a data-free post-training quantization method. Epsilon first estimates how many orders of magnitude separate the distribution's bulk from its maximum. 16 levels, including 0, are then spaced in the log domain. Within each group of size 128, Bank normalizes by the maximum, selects the nearest level, and stores its index and group scale. Linear weights use 4 bits, while layer norm and embeddings remain in higher precision. The adaptive variant builds on a local grid from each group's range. The results reveal that Bank consistently beats uniform round to nearest. On geometry 8 billion parameters, perplexity falls from 7.37 to 7.08. On geometry 270 million parameters, it falls from 57.3 to 36.5. When comparing with NF4, however, no method establishes a total dominance. However, state-of-the-art optimized methods remain stronger. Finally, talking about memory reductions, when we exclude embeddings, memory shrinks by about 7.7 times. To end this video, we can summarize Bank in 3 phrases. Measure the distribution, match the representation, and preserve the sensitive parameters.